Hi guys, how are you? Today we are going to discuss one interesting subject in our algorithm series. We are talking about P, NP, NP complete and NP hard problem. So what does this terminologies mean and how we categorize our problem in these four categories? So basically a polynomial time problem is a problem that I can solve it in a polynomial time, means 1 or log n or n log n or n square or n cubic. I can find or I found an algorithm that solves this kind of problem in a polynomial time. For example, linear search. If I have an array and I need to find one specific item in this array, so searching means basically traversing the whole array and I can find it in n time. Or if the array is sorted, then I can use a binary search and I can find it in log n time. If I want to sort the array, I can sort it by the normal way, insertion sort, and it's gonna cost me like n square, or I can do it through merge sort, divide and conquer, and I can sort it within n log n. So all of this I can solve it in a polynomial time or a polynomial complexity. What about a non-polynomial problem or NP? Basically it is non-deterministic polynomial algorithms. We will talk about deterministic and non-deterministic later, but basically this is a problem that cannot be solved in a polynomial time. There is an algorithm, maybe there is an algorithm to solve it, but exponentially. Like for example, traverse Searles-Person, Hamiltonian cycle, sum of a subset, coloring a graph. I just put it here for simplicity as 2 to the power n, but the main idea is I can solve it in an exponential way. However, I can verify the solution in a polynomial time. What does this mean? If, for example, I'm talking about the Sudoku problem, I have here, this is the Sudoku, and I need to solve it. This kind of game, it take me exponential time to solve it. However, if I have the solution already like this, I can solve it. I can check this solution by n square, like n square, which means a polynomial. I can verify the solution in a polynomial time. So I cannot solve it in a polynomial time, but I can verify the solution in a polynomial time. Okay, so away from this, we are going to discuss another terminology which is called reduction. Or before the reduction part, we are going to discuss the non-deterministic polynomial. To understand what is the meaning by non-deterministic, basically I say if I know part of the solution and I can solve it in a polynomial way, then I can solve the whole solution in a polynomial way. Let's, for simplicity, consider that I want to find an element in this array. We knew by heart that I can do it in n time, but I want to find it in O of 1, a constant time. So by 1, from the first iteration itself, no iterations, I don't need to traverse the whole array. In the first element itself, I get the solution. So basically someone came into the picture and created this kind of algorithm. He said, if I have the element and I get, for example, I get the index of that element in one shot, in one line, then I can say this element exists in that index. Basically, for example, if we are talking about number 6, I want to find number 6. He said if I can find an algorithm which has this function which is called check the array, if I can find a check array algorithm that I give him number 6 and immediately no traversing from the first check is gonna give me number 4. Basically it's gonna give me the index of the array, and then if the if the key is equal to the list of 4, then I found the element and the index is I. If the key is not equal, or there is no matching, then I don't find it. So if I go through this algorithm, the if statement will be O of 1, and then return O of 1, else return O of 1. So if I find the algorithm that's called check the array and I can make it O of 1, then I can say this is a polynomial, not a polynomial, I mean an algorithm of O of 1. But the part that I don't know, which is check array, make this whole algorithm non-deterministic. I don't know currently a function that can get me the index of the value that I'm searching for from the first iteration itself, not the whole. I don't need to traverse the whole array. However, if you can think about something, you can talk to me about it. If we reverse this thing and put it in a hash map, so the value itself, I can from a hash map say the key of 6 is 4 in one shot, in one idea. But copying this array in a hash map itself will take me an n time, because I need to copy and paste each and everything n times to get the whole array. So there is a way to do it, but again, converting this from that state to another state again will take me n times. So I don't know for sure any algorithm that can solve this problem in O of 1. So having this part which is non-deterministic will make me say this is a non-deterministic algorithm. When we talk about non-deterministic polynomial in a bigger scenario, then that means if we go back to these solutions, we can write a polynomial algorithm, but some part of the polynomial algorithm we don't know for sure how to make it in a polynomial way that can solve this problem. That's why it is non-polynomial from now I mean today. But maybe tomorrow, maybe day after tomorrow, maybe next year, someone will figure out a way to change the non-deterministic part to a deterministic part, and in this case this problem will be a polynomial problem. So this is the meaning of non-deterministic. Okay, so we'll go back to non-deterministic and then we will talk about reduction. So basically, if I have problem A and problem B1, and I know solution for problem B1, which is algorithm A1, and I have another problem B2, but I don't know yet a solution for P2. So people were saying, if I can convert B2 to make it similar to B1, then I can use the A1 algorithm, which is the solution for B1, to solve B2. So in this but we need to make sure that the conversion itself from B2 to B1 is gonna take me polynomial time. Otherwise, if the conversion itself is taking more than the time that I'm looking for, then it doesn't make sense. Like the same thing, when I want to find the search in array in O of 1, I said I can do it through a hash table, but converting this to hash table, it will take me n times, so it doesn't make sense. So the same way, if I can convert B2 to B1 in a polynomial time, then I can say B2 is reducible, polynomial reducible to B1, and I can use B1 solution, which is A1 algorithm, to solve B2. Basically, we are saying that B1 B2 is not harder than B1. Basically, B2 is either easier to B1 or the same complexity. Okay, so if we have two problems, one I have the solution for it, and another one that I don't have the solution of it, and the second one that I don't know the solution, if I can convert it to the first one, then I can use the first one solution to solve the second one. So this is basically what we are talking about. Okay, so and now we are going to talk about the last topic and the comparison between NP and NP hard and NP complete and NP, and this is why we are doing all of this explanation. Basically, the P problem is a problem that we said it can be solved in a polynomial time, and then there is a bigger set which is NP problem, which is a problem that cannot be solved in a polynomial time for now, but can be verified in a polynomial time. So basically, P is a subset of NP, because P can be reviewed in a polynomial time and can be solved in a polynomial time as well. And then we are going to talk about an NP hard. An NP hard is basically all the problems that is harder than or the same complexity than as NP. Basically, harder than is this area, or the same complexity of NP is the intersection between both of them. That means if a problem is an NP hard problem, that means all the non-polynomial problem is polynomial reducible to this NP hard problem. That means this NP hard problem is harder than or equal any problem that is NP. And if they are equal, then we come to the NP complete. So basically, the NP complete is the intersection between the NP hard problems and the NP problem. So we can say the easiest one is the P, the harder is NP, the harder is NP complete, the hardest is NP hard. And each one of these is harder than or equal. Like NP hard is harder than or equal NP complete. NP complete is harder than or equal NP. NP is harder than or equal B. And that is the differentiation or differences between them. I hope that video was helpful, and I made it as simple as possible and very short, so it can give you an idea. And maybe in the next session we will do some true and false to get you an idea how to solve the true and false problem for the P and NP and NP hard and NP complete problem. Thank you, and see you in the next session. Don't forget to subscribe and share this video with your friends, and I'm waiting for your comment in the link below. Thank you, and see you in the next session. Bye.